So now after the discussion about increasing and decreasing functions, we're ready for a test that we call the first derivative test. The first derivative test, we're also going to have a second derivative test, and both of them are used for the ultimate same goal, which is to find the relative maximums and minimums on a graph. And so what we do for the first derivative is we actually go take the function, we find its first derivative. And we say if that first derivative changes from positive to negative, then from the previous pages we know that that means the function goes from increasing to decreasing. Hence that means you've reached what we call a relative maximum. So that would imply that you have a relative maximum at that value. And in order to figure out what that value is, again, we're kind of looking at the critical point where the derivative is equal to 0, and we're testing to the left and to the right. And if it goes from positive to negative, we know we maxed out. Similarly, if the derivative changes from negative to positive to the left and to the right of your critical point, then this implies that you have discovered a relative minimum of the graph. So if it was going from decreasing negative slopes to increasing positive slopes to the left and to the right of that critical point, then that implies that I have hit a minimum value. Now, if there is no change, if f prime of x does not change, so you find your critical point, which is where the derivative equals 0, and you test to the left of it, and you test to the right of it, and suppose it was positive, and then still positive. What that means about the original function is that it was increasing, had a derivative of a 0, and instead of turning back down, it went back up, which means you didn't hit a relative maximum or minimum. What some books will call that right there is a saddle point, but our book doesn't. So what we say here is if it does not change, basically what that means is it's monotonic there, it's going in the same direction. I'm still climbing that hill even though I had a little plateau, or likewise I'm going skiing downhill here, and then I have a little area where I'm running horizontal, and then I continue down. Mathematically what will happen on one like this is the derivative will be negative. At this critical point the derivative is 0, but it's not providing us with any relative extrema. So then we would say that we don't have either or neither maximum or minimum. So it's really important to know that what we're finding here are the relative extrema, not the absolutes. Our test for the absolutes is to find those critical points and the endpoints and test them in the original function to see where it's the absolute highest or lowest. What I'm doing with the first derivative test is trying to find those turning points, because what that means is when I change from increasing to decreasing, I must have hit a relative extrema. So let's go take a look at the example. I've got f of x is equal to 1/2 x minus sine x. So the first thing I do is I take the derivative, and I get a half x. The derivative of sine is cosine. And so I take the derivative, and then I want to know where is the derivative equal to 0. And so similar process to what we've done in some other sections. And the derivative will equal, sorry, that shouldn't have an x on it there. The derivative will equal 0 when a half minus cosine x equals 0, which means when cosine x is equal to 1/2. And then again, I have to go back to my domain. We are analyzing from 0 to 2 pi, not inclusively. So I'm back to my unit circle, and I'm trying to decide where is the cosine equal to 1/2. The cosine is equal to 1/2. Sine is 1/2 at 30 degrees. Cosine is 1/2 at 60 degrees, or at pi over 3. So at pi over 3, I have a cosine of 1/2 and a sine of 3 over 2. So that happens at pi over 3. And it also occurs, again, I'm analyzing the cosine, so the x value, so I want another place on the unit circle where the x is a positive 1/2. It'd be negative over here, another negative over here, but right here also the cosine would be positive 1/2, and we have to think about where that is. Well, it would be pi over 3, or you could think of it as 2 pi over 6 in this direction. So we have to go back in that direction. So I'd be at 10 pi over 6 or 5 pi over 3. And I know you guys know how to find those, so I'm not going to dwell on the unit circle there a whole lot. So now what I do is I'm in search of where the relative extrema occur, and I'm not going to make one of those charts. I prefer the sign line. Now, if you use CalcChat or the odds in the back of the book, they're now going to go make a chart. I like to lay it out on a derivative sign chart, and I am not actually starting at negative infinity or infinity. I'm going to go like this. My chart is going from 0 to 2 pi non-inclusively. I have the derivative being 0 at pi over 3, and I also have the derivative being 0 at about 5 pi over 3. And what I'm going to do is I'm going to test where the function's increasing and where it's decreasing. I test it in the derivative. So I go back to the derivative right here, and I'm going to do a sign analysis. So, and again, I should have not an x on there for my derivative. I don't know why I have that on there. All right, so I'm going to go run a test on here in these intervals. So I need some angle between 0 and pi over 3 with which to test. The most obvious ones being either pi over 6 or pi over 4, whatever you prefer. I'm just going to choose pi over 4. So I run a test on pi over 4 in my derivative, and I analyze the sign of it. If I were to do 1/2 minus the cosine, minus cosine of pi over 4, it'd be 1/2 minus root 2 over 2. This is bigger than 1, so it's going to go negative. Now, what's interesting is, although you can't assume that they always alternate, for the sine wave, you kind of can assume that it's going like this, because you know there's no places where it plateaus and then goes back up. So it does go from positive to negative, increasing to decreasing. So although that technically you're not supposed to assume that they alternate, if you really understand graphically what's going on, they will. So I really don't need to test for one like this, where I know what the sine wave looks like. So the question was, where's the relative extrema? Well, what this is telling me is that in this part of the graph right here, the function was decreasing. And then it hit 0, bottomed out, and was increasing. So what that tells me is this provided me with a relative minimum. Likewise, so it was going down, it hit 0, and then it was going up, and then it went down again. So this 5 pi over 3 is providing me with a relative maximum. So when I answer this question, I need to write my answer. It says find the relative extrema. It doesn't say what is the extreme, because then it would be a y value, but I want to know where it is. I want to find its location. I now know that my relative min, I'm going to write this, relative min is at pi over 3 comma something. I also know that I've got a relative max at 5 pi over 3 comma something. And to find where it is, you need to go back to the original function. I used the derivative to help me find properties of the original function. So I'm not going to go do the arithmetic, but pi over 3 would have to go in here, and I'd see what y value or what function value it poops out. Same thing with the 5 pi over 3. So again, with the process here, what I'm doing is I'm using where functions increase and decrease. So I'm finding a derivative. I'm finding where they're positive and where they change to negative, or negative and change to positive. Those provide me with the relative maxes and mins. So let's go do one more. I've now got x to the 4th plus 1 over x squared. I don't have a good concept of what the graph of this one looks like I did with the trig one. So this is going to require some full analysis here. I do know that I need to go find where the derivative is equal to 0. And what I've got here also, you'll notice, I know there's an asymptote here, discontinuity, but there's a vertical asymptote at 0. That's important with the graph because it can lead you to some false conclusions. Or let me just draw what I mean by that. A function can be increasing to the left and then decreasing to the right of an asymptote. And on your sign line, what's going to pop out of there is a positive value and a negative value. So you're going to be tempted to conclude that the function maxed out in between them at 0, but it actually didn't because there was an asymptote here. So we've got to be very careful how we organize our information with this. When I make my sign line, I'm going to put 0 on it, but that's not where the derivative is equal to 0. I like to put a little infinity on there, so I know I'm actually heading to infinity there. So I've got asymptotic behavior, which won't provide me with any relative max or min there. So be very careful watching your domain. I didn't have to do it on the last one because I didn't have any place that would cause a discontinuity on that graph. But on this one I do. I have a vertical asymptote at x squared. So now what I'm going to do is take the derivative, but we talked about last chapter how when you take the derivative with the monomial on the bottom, it's much easier to break it up like this so that you're not doing the whole quotient rule on it. So really I'm taking the derivative of x squared plus x to the negative 2, which would be 2x minus 2x to the negative third, if I were to clean up my derivative. So what I've got going is 2x minus 2 over x cubed. And my goal is to figure out, well, where is the derivative equal to 0? So I need to take and get a common denominator, and you can go crisscross, I don't know how you do it, but I'd have 2x to the fourth minus 2 over x cubed is what equals 0. Now, my denominator I've already taken care of. That at x equals 0, I know there's no derivative. It's not because of one of these. It's because of the original function, I had a discontinuity there. So there's no derivative, not because of a cusp, but because of an asymptote. So, next step, what I need to do is figure out, well, what makes the numerator equal to 0? That's pretty obviously going to be at plus 1 and minus 1. You could go solve it, but trust me, that's what you're going to get. So x would be plus or minus 1. So I'm going to put a negative 1 here and a 1 here. I'm going out. I'm not being blocked off on any sort of a closed interval or open interval here, so I'm going to put the infinities at the end of it. And I'm going to go see what happens to my derivative in these spots. And when I go do that, I'm kind of starting to talk fast because I only have about 2 minutes left here on my time, and I want to finish this problem off. So when I test a number, remember what I'm testing it in is in the derivative. So I'm testing it in, I would say probably the best spot, where would be the best testing spot? Maybe right here, twice x minus 2 over x cubed. You're testing it in your derivative. So when I take a negative, say 2 or something in this region, that'll be a negative, probably a negative 4, and then it'd be minus, and then it'd be 2 over, a negative 2 cubed is negative 8, and it'd be addition, but that's going to end up being positive. You're just running a little test on all of these. And so, just for time purposes, I think, I'm going to tell you that this actually goes plus, minus, plus, I believe. But let's talk about this. What this means is it's decreasing, then increasing, but asymptotically. And this one's decreasing and then increasing. If you go graph that on your graphing calculator, if I were to even put this on an x, y coordinate system, you're going to see 2 u's going like this. So really what this is telling me is that I have 2 relative minimums there. So I've got a relative minimum here and a relative minimum here. That looks kind of like a funny graph. It looks like a pair of breasts, but I'm sorry, I gotta erase it. All right, I can't look at it. All right, anyway, so we had a relative min and I'm sorry, 2 relative mins at 1 and at negative 1. And to find the y values, we'd have to go back to the original function and put those in. So that's it for this part of the notes. I'm so sorry about that. And you guys can go ahead and start work, and what I'll do is tomorrow I'll pick up with a little bit more notes, probably one more 15-minute block, and we should have section 3.3 covered. You guys have a great